This is number 78 in chapter 15. 78 has multiple parts, and it's looking at mixtures of acids. And I'm only going to do part B and part C, and then I think hopefully that will give you the point. And so with mixtures of acids, we basically have to determine strong versus weak, right? If the weak acids aren't going to impact the pH if it's paired with a strong acid, and so really that's what we need to do is when we look at a mixture, what types of acids are actually in the mixture. And so for part B, it's talking about two concentrations. We have 0.02 molar HBr, and we have 0.015 molar perchloric acid. Both are strong acids, right? And if both are strong acids, that means that our concentration of HBr initial would equal our H3O plus concentration. But the same could be said for our perchloric acid. Since both are strong, both completely dissociate. And so really we just need to take a sum of those two. So if we have HBr as 0.02 molar, we would use that to find the total H3O plus concentration. That's the contribution from HBr. The contribution from hypochloric acid is 0.015 excuse me, molar. And so when we add that up, we get a value for our H3O plus to be equal to 0.035 molar. Ultimately from that we can get the pH, right? The pH is equal to that negative logarithm of the H3O plus, and so our pH is equal to the negative log of 0.035, which is equal to 1.455. So that's the pH for a mixture of HBr and perchloric acid. Again, both are strong, so both completely dissociate. That means we can just relate the initial concentrations directly to the amount of H3O plus that's generated from each one respectively. We take the sum, we then get the pH. So that's part B, which is really a mixture of two strong acids. Let's look at part C. Part C looks at a mixture of 0.095 molar HF and 0.225 molar, this is actually phenol, HC6H5O. These are actually two of the exceptions that I kind of talked about. This is actually an exception that's not a CO2H. This is actually what's known as phenol. And then we have hydrofluoric acid, and you might say that, well, hydrochloric, hydrobromic, those are all strong acids. Hydrofluoric is also strong. Hydrofluoric actually is not a strong acid, it's actually weak. And this has to do with the anion of fluoride. F minus, since the atom of fluorine is so small, and there's a lot of electron-electron repulsion, so the anion really isn't that stable as far as F minus or fluoride is concerned. As a result, we really have two weak acids here. And we could actually substantiate that again by going to a table of KAs. And so if we go to a table of KAs, we can see that HF has a KA equal to 3.5 times 10 to the negative fourth, while for phenol the Ka is 1.3 times 10 to the negative 10th. So both of these have Kas, and both of these are less than 10 to the negative fourth, so they're both weak acids. Now it's really just a question of, is one stronger than the other? And we know that, right? Because this is a much larger Ka than our Ka for phenol, 10 to the negative fourth versus 10 to the negative 10th. So that means that this molecule will have no impact on pH due to the extreme difference in those Kas. So as a result, we really just need to worry about the Ka for HF, because it is so much greater than the Ka for our phenol. Once we realize that, we really just need to solve a standard acid equilibrium expression. Here would be the equilibrium equation, or I'm sorry, reaction, and so we would want to determine ultimately our H3O plus, so we can then determine what is the pH of this mixture of acids. But again, we only care about this Ka because of the fact that it is the much larger Ka. So if we kind of erase some of the phenol material here, I'm going to make some room. Right, we need to have then a nice table. Right, and those are our initial conditions. We have 0.095 molar HF. Again, even though the concentration of phenol is greater, we don't care because of the small, very, very small Ka. We have no concentration of our products. That tells us our change is going towards our products. And so that is our ice table. We can plug that into our Ka. Remember, our Ka was equal to 3.5 times 10 to the negative fourth, and that is going to be equal to our H3O plus times our F minus over our HF. Here's where we need to make an assumption. We'll assume that that goes to 0 because we have a very small Ka, and we also have an initial concentration of starting material. Since starting material is favored by our Ka, that means that change is going to be small relative to it. And now we can solve. So once we have our 3.5 times 10 to the negative fourth is going to equal our x squared over 0.095. Right? That x squared is going to be equal to our 3.5 times 10 to the negative fourth times our 0.095. And we want to take the square root of both sides. And so when we do that, we get our x, which is equal to H3O plus, which is equal to 5.76 times 10 to the negative third. From there, we can get our pH. pH is 2.239. So that is our pH, and really the pH is solely resultant from the HF, again because the amount of H3O plus that's generated from the other acid, the phenol, is so insignificant because of the drastic differences in Ka. We should probably check our assumption just to make sure it's valid. So our 0.095 minus our change and when we do that and turn it into a percent, we actually get 94%. So this is close, not quite 95%, but I think we're close enough for this one. That's going to be pretty close to the pH. That is number 78C, and again, it's recognizing that when we have weak acids, in particular two weak acids, it's going to be the one that is stronger or has a larger Ka that is going to designate the actual pH of the solution.